of the Quangan people. And my talk today is about radiofrequency superconductivity for accelerators. So I started giving you a little bit of an overview what this all to be about. I mean, okay, so radiofrequency for superconductivity for accelerators. I put it like, let's break it apart a little bit and make a talk out of this thing. So first of all, I talk a little bit about the accelerator research program we have together with Triumph, the lab in Vancouver together, what we're doing, and then break down like where do we use superconductivity in particle accelerators, but obviously there are other applications of superconductivity. I will talk a little bit about that as well. Before we dive into fundamentals, so we're talking about radio frequency superconductivity, but to understand that, we first of all need to understand how you actually use radio frequency cavities. So I have one right now here. This is a prototype from CERN. And we need to understand how we use cavities and what is superconductivity, and then bringing that together to understand what is really radio frequency superconductivity, why do we care about it, what's so specific about it. I then have to talk, split up a little bit into the engineering and the fundamental material side of things, and in both cases, I present some students' project we have in that regard. Okay, let's get into that. So we have a graduate program at UVic together with Triumph, and it has grown significantly over the last year. So we have now 14 graduate students, most of them at Triumph. We have some at UVic, and I also work with a company which is in the Kootenays in Nelson. So in total, 6 adjunct professors, which one of them is at the company in DP, 6 are at Triumph. Also, if you're interested in the field of particle accelerators, we have a graduate course which is taught by the adjunct faculty. It's also broadcasted nationwide. People have taken this from different universities, so if you feel like this is something you want to add to your education, we can set you up with that. So people have taken it for credit as well, so this is possible. You can ask me about that in the end of the course. Right, then at UVic I focus a little bit on the undergraduate side of things. So at Triumph, most of the accelerator program was more geared towards graduate students. I offer an undergraduate lecture course and also undergrad and a graduate project as well. So we have no accelerators at UVic, but this is something which maybe not too useful, especially particle physicists can probably relate very well to that. Experiments are huge, centralized, but accelerator research is possible. We do several things at UVic now. So some things, it's cryocooler-based fundamental SRF research, SRF superconducting radio frequency. Cryocooler means I don't really have to work with cryogenic liquids, makes my life easier. Then we do surface and material science studies. I work there with a local electron microscopy facility. So these are all other professors I use together with here in the brackets. And I look into application of superconducting radio frequency also for quantum computing. You can use potentially this cavity to learn about the quantum world as well. Come to the very end of my talk briefly. Also, we do beam dynamic studies, simulations. So overall, we do beam simulation, systems development, material science aspect, and also fundamental studies with really dedicated research equipment. These are some applications of superconductivity. So you could potentially build a magnetic levitation train, which can go as fast as 600 kilometers per hour. And if you would run that into even in a vacuum tube, you would basically have a completely frictionless system. Got to get your brakes right, I guess. And energy, fusion. Fusion is rather what you do is you confine a plasma. You need strong magnetic field to do so. So there, fusion reactors are based on superconducting magnets. In healthcare, we have the magnetic resonance imaging, which is based on nuclear magnetic resonance. Also, material science. We have superconducting magnets at Triumph. Not for accelerators, but for some experiments as the beta-detected nuclear magnetic resonance. This is a type of nuclear magnetic resonance, only that it's billion times more sensitive and it's depth resolved. So you basically could do NMR depth resolved on the nanoscale, billion times more sensitive. We use this also to characterize material for accelerators where it feeds back. Particle physics. The ATLAS experiments, for example, use superconducting magnets. We have here the inner solenoid, and the outer toroidal field is actually the largest toroidal magnet in the world. So all these applications rely on the fact that you can transport much more current through a superconducting wire, also lossless, than you can to a normal conducting wire. Just to visualize that, I have two wires here. So this is a normal conducting, just a piece of copper wire, and this is a superconducting wire here. Can you see it in the back? Okay, good. I mean, it's rather thin, yeah. But I mean, these two wires, okay, they can transport the same amount of current. And this one is lossless. Well, you have to cool it, right? Superconducting, non-conducting wire. And this is why, okay, you can imagine, like, for a magnet, you need to have many windings, yeah? And again, obviously, you can do a lot more with that. That's why, okay, all these applications, they basically rely on the fact that you can transport a lot of current through a thin wire. Coming to accelerators or magnets, yeah, definitely. So this is how an accelerator looks like. So at the end of the day, an accelerator is a big vacuum tube, and in that you have magnets which keep the particle on track by bending it around, and then you need focusing magnets. You think, like, we don't accelerate a particle at a time, they come in bunches. 10 to the 11 particle at once, and okay, they have all the same charge, so they don't want to stick together. So basically you have to force them. This is also done with magnets, focusing magnets or quadrupole magnets, if you look at the shape of it. So for example, the LHC tunnel is 27 kilometers, and it is basically filled with superconducting magnets. 27 kilometers of superconducting magnets. This is how it looks like. You see here, now it has to be cooled down, so this is all at 1.8 Kelvin. Interesting thing is, so this wire, if you look at it, you would see like it just looks like a copper wire. Why it actually is from the outside. It's a superconducting wire, but superconducting currents, they only flow on a very thin surface, a couple of, about 100 nanometers, depends a bit on the material. So how it is being built is you use a copper matrix, and then you have very small filaments in there, basically maximizing your surface area. Like if I make a big superconducting wire, it doesn't really help a lot because it only flows on the surface. Everything would be with a thick superconducting wire would not help. Okay, so far everything wires. This is not what I work with, so these are actually sheets. The NIOM sheets. This is a radio frequency cavity, and this is used in an accelerator really to accelerate. You can basically think about there's a voltage from here to here, and the particle passes through, and then it gains some voltage, and then it gains energy. It's a transformer, basically. Electromagnetic energy is being transferred into kinetic energy of the particle. Right. And it uses, instead of a DC current, it's an AC. So how does it work? So I have here this little graph here. So what you want is an electric field on axis. So you need my electric field pointing that way. This is where a particle would go through. Yeah? Particle comes here. And the electric field is between here and here. So this one is here thin. Yeah? So the electric field cannot propagate. It's an oscillating system. Yeah? My electric field is constantly changing direction. It's a radio frequency device. So it's oscillating in here and exponentially decaying in here, my field. So only in here. So the idea is that a particle comes here, reaches that point. In that moment, the electric field needs to point in the same direction, and it has to leave before the electric field has turned around. Otherwise, it would be decelerated. So the length, this is the 3 gigahertz cavity, and the length of this cell here is just optimized that the particle, which already is very close to the speed of light, just travels from here to here in half an RF period. Yeah, so the gigahertz, you can work it out, 3 gigahertz, how long it is, speed of light, and then you would get that. Yeah. This is how it is. So like if you have an accelerator, a linear accelerator, you have linear and circular accelerator. A linear accelerator would be basically 50 kilometers of those. That would be the longest one if we would build ILC. But the longest one right now, a free electron laser in Hamburg, it's basically, 3 kilometers of that. Okay. That's it. Okay, so we're done. We can say we're done here. That's okay, though. Okay, right. So this is the function. This is how it works. Oh, you see. So cavities, what they are using is an alternating electric field to transfer energy to the particles. But Maxwell's equation will tell you, as soon as you got an oscillating electric field, that implies that you also, so the Faraday's law of induction, you also have a magnetic field. Okay? Electric field that way, magnetic field that way. Okay? So this device now confines the electric field, the electromagnetic field, specifically the magnetic field, which would be here. And how does it do that? Basically by creating surface currents, which just oppose that. So it kind of like, yeah, that's how an electromagnetic resonator works. So through Ampere's law, you got to current them to do so, and Ohm's law will tell you that you have some dissipation of that. Okay? So before I said that superconductivity means zero resistance. Yeah, this is true as long as you have a DC current. As long as you have an alternating current, this is no longer true. I will tell you why that is the case. I'll run a little bit through some superconductivity basics to show that. Also, you might have seen superconductors or heard about superconductors which can run at liquid nitrogen temperatures, 77 Kelvin or above. This is niobium, very old material in a sense. We have to use liquid helium. Why? Why we don't do that? These are basically some questions which I like to answer, going through some fundamentals of superconductivity. But let's start from the very beginning. Historical overview of superconductivity. It was discovered in 1911 by a person called Heike Kamerlingh-Onnes in Netherlands, in Leiden. Yeah, so that was just 3 years after helium could be liquefied, because you need really, really cold temperatures to get to superconducting state. Then 22 years later, it was discovered that superconductivity is actually more than just perfect conductivity. There's also something else, a Meissner effect, which you see it's demonstrated here. So you have here a superconductor and a magnet is floating on top. Well, actually a pretty cool experiment where you put a magnet on top of a superconductor and you cool it down, and then it will magically float up. And at the moment it's getting cold enough. This is what's the Meissner effect. And you see, this effect, it can now be demonstrated using high temperature superconductors and liquid nitrogen. This was only discovered in 1986, this type of superconductor. But there are a type of so-called type 2 superconductors, which was only discovered 40 years. We only knew after the discovery, we knew there were two types. And only these have basically technical relevance. I could not make a wire, a magnet. I could make a wire, but I could not make a wire out of a type 1 superconductor. So very interesting. So like I have this wire here, and it can take a certain current. Let's assume it would be lead, and I do that. Okay. Now it can take, if I wiggle it around like that, it can only take 1/10 of the current. Weird, right? Why is that? Like that, can take a certain amount of current. I turn it around, turn it so that, and it can only take 1/10. It's a magnetic field. These classical type 1 superconductors, they don't like magnetic fields. So only these type 2 superconductors, which can deal with that, became technically important. Interesting thing here, discovery 1911, and the understanding, the microscopic understanding, only came almost 50 years after. 1957 is when we got the theory. There are some other effects which are really relevant, not so much here for my talk. It's more relevant to the quantum application, magnetic flux quantization as a Josephson effect. Just here to mention for completeness, going too much into that. Okay, discovery of superconductivity, 1911. So here's a plot of the resistance versus temperature. And before 1911, people were arguing, what's actually going to happen when we have a piece of metal, you cool it down? We know resistance drops. Okay? So, but what's happened? So Dewar argued, yeah, okay, if you just reach a temperature which is cold enough, your resistance should go to 0. Because I already figured out it is through basically through scattering processes, and I thought, like, okay, if everything stops moving, basically, okay, you would have no resistance. But then Kelvin argued, yeah, well, but I mean, your electrons will stop moving as well. So yeah, okay, you reach at some point the minimum, and then it should go up again and actually become infinite. Metzner had somewhat figured out best and realized, okay, there's these two systems. There's the lattice contribution and there's the electronic contribution, and says, okay, you should reach a finite point. So Kamerlingh-Onnes made some experiments first with gold. So this is from his Nobel lecture, and you see I just mark here the gold line, and realize, okay, good. I go to a higher purity, my resistance will drop. And so then he estimated, okay, if I only can get it pure enough, eventually I should get here. But he just couldn't get gold pure enough. So he said, okay, good, let's use some other material. So what can you purify very well? Well, something which is liquid at room temperature, distillation. You can use distillation process. So we need a metal, which is liquid at room temperature, and it's found in mercury. Yeah? And so I tested mercury, comes down, but here comes a surprise. It's not gradual. So what happens is actually, it is really a sudden drop. Better here in the close-up. There's a sudden drop here. Instead of a gradual increase, I found a sudden phase transition. And so a new phenomenon was discovered. So in 1903, 20 years later, we found out, yes, there is actually something very different from a superconductor to a perfect conductor. You can look at Maxwell's equations and assume perfect conductivity. Basically, you replace Ohm's law with free acceleration in the end. And then you get a certain prediction how a superconductor would behave under magnetic fields. And you have to look at two scenarios here. Scenario one is I apply field first, and then I cool, or I cool first, and then apply the field first. So let's say I do cooling first, and we have this ideal conductor. I don't want to call it superconductor, because, okay, it doesn't, yeah, it's just right now a model, Maxwell's equation plus perfect conductivity. I would see, like, okay, the field would be expelled. Yeah? A very good conductor, like very good copper, would not do that. Yeah? Because, okay, still, as long as Ohm's law applies, you will not see that. Copper will not behave like that. Okay, and then you got all the field being expelled. Meissner effect, yeah? So again, you bring your magnets over that, you can really demonstrate that, put it on top. But what happens if I apply the field first, then I cool, all right, and then the magnetic field would just remain constant when I turn the field off. So, but a superconductor behaves differently. So that part here, that's fine. That's what superconductor does. But if I apply the field first and then cool it, it gets also expelled. And this is not what we would expect just from a perfect conductor. So what we see that basically we see that superconductor activity is a phase transition here really. So the final state does not depend on the order of cooling or applied field. Yeah? Both cases we end up here. Although it means a superconductor is basically a perfect diamagnet. Yeah? So it will expel all the field. It's a perfect diamagnet. So this is called the Meissner effect. Complete expulsion of external magnetic fields. And it also means, okay, that I have no magnetic field, I have no current in the interior, right? So supercurrents only flow on the surface, and they decay over length scale, which is about 100 nanometer, depending on the material. And again, if you remember here, that's why these wires are built like that. Yeah. If you make them, each filament and let them thicker, it would not help. Okay, so 1957 now, 46 years after discovery. Okay, let's see what we found out, and come up with a theory for that. So we have zero resistance and the Meissner effect. There was something else which was called coherence. It's a non-local relation between current density and electric field. So like for Ohm's law, it would tell you, okay, you know the current at some point, and that tells you the electric field at that point. But in a superconductor, if you know one at one point, it will not tell you exactly what's the field is there. So you need to take into account a wider area. That's a coherence involved in that. That was found in energy gap and in exponential specific heat. So I can show that here. So this is how the specific heat of a normal conductor looks like. Yeah, so basically, it follows a power law, T to the power of 3. Yeah? But for a superconductor, it looks very different. It's exponential, and then has this drop here. So what does it suggest? This suggests that there is some sort of a condensation process, and some of the electrons don't contribute anymore. to the specific heat capacity. Yeah. Then also what's interesting, there was something which an isotope effect. So this is a transition temperature. It's basically the temperature where mercury becomes superconducting, and this is it's a function of the mass. Yeah. So if you look like have very heavy isotopes, very light. So the good thing is about that mercury, it has several stable isotopes, so you could really do that experiment. So it was good, and you see how well. So like the lower the isotope mass, the average isotope mass is, the higher the transition temperature. By the way, people are, when they're looking into room temperature superconductors, what material are they looking for? Hydrogen, or materials with hydrogen. Yeah, you see the lighter one is up here. So transition temperature, the lighter it is, and the lattice would rather support it. What does it suggest? So this suggests that the lattice is important for superconductivity, and this is what the BCS theory then incorporated. So the idea is that you have a pairing of electrons into pairs. So basically create an attractive interaction between electrons. Obviously electrons normally they repel each other, same charge, but through interaction with the lattice, it's kind of here depicted a Feynman diagram with a photon interacting with them, they create an attraction. So if you have two electrons, what you got, you have a boson. Yeah? Single integer charge. All Cooper pairs now condense into the same ground state. A Cooper pair is just two bound electrons. And they can form a coherent wave function. A coherent wave function will not scatter with the lattice. We got zero resistance. That's the explanation. So what about, we said that there was a coherence. And we thought, like, what is the size of the Cooper pair? How far do they interact with each other? And you can make a rough estimate for that. This is not 100% correct here, but it gives really the right order of magnitude. If you just think about what is the relaxation time of the lattice and compare that with the Fermi velocity, which the electron moves, and then you get about 100 nanometers. This is really what actually coherence length is, how far these electrons can communicate to each other and form a Cooper pair. Okay, so far everything that was about DC superconductivity. But here, what we have here is radiofrequency superconductivity, and that has some particular things. So, as I said, DC supercurrents are lossless, but what about AC currents? So, for AC currents, what we got is we got these Cooper pairs. But not all electrons will form Cooper pairs. Some, like if you have a temperature above 0 Kelvin, well, we have, you always have, you have some electrons being excited in a state. So like not all electrons will form Cooper pairs. You got these, okay. So now the Cooper pairs, they have no resistance, but they have inertia. So under a radio frequency field, what has happened, they will induce an electric field in the material. Now if I have an electric field in the material, and I have normal conducting electrons there, well, these electrons will move under this radio frequency field, and these normal conducting electrons, they can scatter. They simply obey Ohm's law. So we got normal conducting electrons, Fermi distribution actually, the normal conducting electrons, magnetic electric field induced, Ohm's law, and this gives me my dissipation. My dissipation is proportional to the number of normal conducting electrons, which is proportional to this Fermi distribution. Now this is why under radio frequency fields we have intrinsic losses. Okay, now material choice. Let's look, what material are we going to use? So ideally you want to minimize that number, so you want to have this one here, the energy gaps. It's just the energy which separates the excitations from the ground state. Yeah? And it turns out that according to this BCS theory, they're proportional to each other. Yeah? So basically, the higher the temperature where the transitions happen, the larger is the energy gap between. Okay? Take that as is. And so what we're looking for a material which has a high as possible critical temperature, right? Okay. All right, shopping list. So, pick one. That looks good. Okay. This is a critical temperature as a function of the year of discovery and some Nobel Prizes won along the way. It's Discovery 1911, as I said, mercury, and then quickly lead was found, niobium, 1920. 1930, 31, yeah. And then, okay, only in 1986 you got some materials which had these very high critical temperatures. But what are we using? This is niobium, plain old niobium. We're not using these fancy superconductors. Why? Okay, for some reason some of these are ceramics, or high temperature superconductors, which makes life harder for manufacturing. But there's more to it. I mean, you could use, there are some superconductors which would be have much higher actually temperature, but still using niobium. For that we have to understand, this is covered right in the 50s, that there are two types of superconductors. So let's start with the type 2 superconductor. Type 2 superconductor, simply as I said, okay, if you put a magnetic field to it, it will basically lose the superconducting state. It will become a normal conductor again. They don't really like magnetic fields. So this is a plain, simple type 1 superconductor, just as mercury or lead. Basically all elements except for niobium. Niobium is a debate whether it's a type 1 or type 2. We don't really, depends who you ask. Yeah. This is active region that we got. So basically as soon as you apply a field, it will get normal conducting. However, a type 2 superconductor has what we call it a negative surface energy. So what it can do is it can create very small normal conducting parts, where in these normal conducting parts it would allow flux to enter. Yeah? So basically it does not expel all the magnetic field, it lets some in while remaining the majority of the material to be in a superconducting state. This is what a type 2 superconductor does. So what you have then you have some flux in there in the form of fluxoids, flux tubes. They're about a couple of nanometers in diameter. So under DC fields, these are pinned. They don't really bother us. The supercurrents find their way around it. So it can be still lossless. So these type superconductors are lossless even if some flux is in. So that's why superconducting magnets, they're operated between BC1, BC2. BC1 is just where the first flux tube had entered, and BC2 is where superconductivity is ultimately lost, basically when flux tubes are going to overlap. Called the state in between a mixed state. Kind of see as depicted, you see like the field is kind of squeezed in through these flux tubes. And we see like, so it looks at material. So lead is a type 1 superconductor. It doesn't have a BC1 or a BC2. It doesn't make sense, yeah? It just has simply one field. For niobium, for type 2 superconductors, you can define such fields. And yeah, for niobium I have numbers, but this is not the cleanest niobium. The question what the cleanest is, whether it's type 1 or type 2. So this BC1 is very high. This is the highest of every element, of any material, actually. So there's 170 milliteslas. And this is where we need to operate. We need to operate that in the state where no flux tubes in there. You see, for a material like niobium titanium, so that field is very low. So it wouldn't be interesting to build an RF cavity out of that. So this is niobium, and here this is niobium titanium. Okay, for a wire it's fine. It can go up to 11 teslas or something. A material which could be interesting for both, for wires and for cavities. Actually, both used already for wires. For example, the LHC, the inner focusing system where you need very strong field just close to the detector, as where we use, we can go higher. There's a fourth line here, as we call the superheating field. So superheating field is how long could this flux-free state persist for a perfect surface. So what's superheating? Maybe, have you heard about superheating water maybe? So, you know, it can heat water above 100 degrees Celsius. Okay, if you have no nucleation in a microwave, you can put a spoon in, it explodes. Looks pretty cool. And here is by superheating we mean that we can have a Meissner state above, well, I mean, in the end of the day it means it is energetically favorable to have a state, but you still need to make it happen somehow. This is a nucleation. A nucleation in our case means a flux needs to enter. That's a surface barrier. So niobium can go, about 50% high, depending on purity a bit. And this is niobium titanium could even go a little bit further. But okay. But for now, coming towards the end of my talk, let's keep it to niobium for now. So these are niobium cavities we are building for accelerators starting from the 18th and in several countries. And this includes also several ones in Canada. So this is a total voltage growth. It kind of like that would be if I would add all the voltages. So one of that would be a megavolt in the ideal case if you all end that up. So that's you got in the total gigavolts if you would put them all under each other. And there's a Canadian contribution to that. We got 2 accelerators actually which use superconductivity. We got Triumph, 2, and we got the Canadian light source. Putting that on the map, all on the westish part of Canada. Triumph, we got 2 accelerators, and then we got the Canadian light source as well here in Saskatoon. This is a look at such accelerators. So just to give you a little bit about the complexity. So obviously you need to cool it down, otherwise it will not work. So we got SRF accelerator bare cavities. You put that into cryo modules, which basically get the thing cold. Put all the cryo modules together, you got an accelerator. So just to give you an overview of such facilities, how they look like. So what you see here is that at Triumph we use it for different applications. So this is an electron accelerator. So this one is also optimized for electrons. While here this is for radioactive ion beams, so heavy, really heavy particles. And so it's different. So yeah, and it needs different types of accelerators. I just try to explain briefly what it is. So basically, the interesting thing is that the frequency at which it resonates depends only on the diameter. So if I make it shorter or longer, my frequency will not change in that particular mode. TM010 mode if somebody is with electrodynamics. But the length, the length determines how long is basically set for the particle just to leave before the field has changed. So let's say I have a particle which runs at half the speed of light. How would I modify that cavity for a particle which runs at half the speed of light? I can. The length I can alter, right? Make it longer, make it shorter? Longer or shorter? Shorter, exactly. Yeah, shorter. So this is how a proton cavity looks like, because it takes basically more time for the same distance. So we need to make sure, okay, it gets out in time. So this is how a proton cavity would look like. But what did I do? What if I do if I have heavy ions, like, well, we use a Triumph quite a bit. That thing is at some point becoming very, very thin. That is not very practical. Yeah? So what we are using then is a quarter wave type of cavities. Think about that. So think about this is about a wire which is open-ended at one side and then shielded around, like a coax cable in the end, like an open end of a coax cable. Maximum magnetic field here, vanishing magnetic field here, electric field maximum, minimum here. Yeah. So what you do then basically is the electric field's pointing outwards there, and you have 2-gap acceleration. You come in here, you get the first kick. In here is basically the particle goes into the center where it's shielded from the electromagnetic field. So basically it has time, wait for the field to turn around and get the second kick. Yeah, this is how it could look. That's how it looks like. We got here cryo model 1, 2, 3, 4. Cavities in there. In between is a magnet. That's for focusing. Also, that one is also superconducting. Interesting thing is if you look through, if you kind of would go through the accelerator, you could really see how it changes. So for at the beginning, low energy, low velocity, it looks like that. So very thin, and then this part in the middle becomes bigger and bigger as the particle is speeding up, because it can travel a longer distance before the field is turned around. So the electron accelerators are pretty boring. So like you said, like really, literally, the X-ray free electron laser in Hamburg, okay, so it's 3 kilometers of that. Like for heavy ions, you have to change your shape along the way while the particles are gaining velocity. Okay, so performance of superconducting cavities. We know already that we have some dissipation. They are not lossless. I should point out here, an MRI machine, for example, does not have a power supply, only to ramp it up. Otherwise, it's becoming a permanent magnet which only has to be cooled. Because zero resistance, how long does a current flow? forever. It's actually the most stable current you can actually create in that because there you have no losses. Yeah? So basically what you do is you turn it on. You have a little wire there which you heat up as long as the power supply is on, and then you make a switch and then you run it. These things have losses, but they're pretty good. So just okay here. It's also an an acoustical resonator. So you see, and it works actually pretty good as an electromagnetic oscillator, even so it has losses. But if it would have the same quality factor, everybody quality factor, yeah? Quality factor is just the number of oscillation any oscillating system is going through because the energy is going to 1 over E. You can have it for a pendulum or anything. But if the quality factor would be as high for the acoustic mode as it would be for the electromagnetic mode, basically what I could do that, okay, put it here, and then come back next year. And you would still hear it. You would still hear it. This is how good it is. Quality factors 10 to the 11, 10 to the 12 is that one. Okay, but it's hard to get there. Practical. The higher my accelerating gradient, you could probably say that, okay, it's a voltage from here to here, and if you define it by the length, that's my accelerating gradient. At the end, it's a voltage, yeah? Okay, so this is my defining thing, accelerating gradients. The accelerating voltage by the cavity length, or more practical, if I have a single charge particle, it's basically the energy gain from here to here. Voltage times charge, okay, if it's more than one charge, it will be more than that, but if it's, energy gain of a single particle divided by the length. This is what we want. We want this one to be as high as possible. We want to go here. And then the other thing is the quality factor. The quality factor, I said already, oscillating system, so how many oscillations can go through, is proportional to my power dissipation. I want to be as high as possible. So ideally, I want to be here, in this part. But unfortunately, not always you get there. You need like very, very good preparations to get that. And there are what we call extrinsic and intrinsic limitations. So extrinsic is, I think it's not prepared in a proper way. And unfortunately, we often end by that. One particular one I want to talk about is field emission, which can be, what's field emission? So you have a high radio frequency electric field. What it can do, basically, it can rip out electrons from the surface. Yeah, there's like a sharp point. You got the field emission there. Yeah, these electrons then will be released, and they're creating X-rays when they hit the surface again. They're ripped off, hit the surface again, and they create heating by that. So what we need to have clean assembly and high pressure rinsing with ultra pure water, and then, okay, then you get a cavity which is performing as we want. Unfortunately, clean assembly prevents the field emission, but sometimes it reoccurs. So it's hard to keep a full accelerator completely clean. So can be dust or something there. So here's here an example. Why is it so important? So like, if I get field emission, my accelerating gradient drops, and then also my electron energy, which I can get out of there. So what we're using that as a driver at Triumph. That means basically all the electrons are being shot onto a target, and then they're creating what's called secondary particles through fission. Yeah, and we want to get as much fission products out of it as possible. We're running at 30 MeV. And if you lose the energy, okay, you see, like, it's a logarithmic plot, when we lose really performance of the whole Triumph accelerator complex. The drivers is really where the whole process starts. Huh? So how to prepare that? I mean, it happens really. I mean, this is a plot, this is in operation. So a clean cavity, all right, 10 megavolts per meter, even higher than that. Great, good. So that's where we operate. But it sometimes happens during operation that it suddenly drops. All right, and this is bad. I mean, this is a long process. You see, everything was done in a clean room assembly, and you need to get down into the hall, get the thing out, get it into a clean room, clean it up again, and fingers crossed, put it back in, and hope it works. Right, so this is a cumbersome thing, and we hope a better way to do it is we're trying to do plasma cleaning on it. It could be done in situ, and instead of about 2 to 3 months is the estimate what it takes to get it out and in again. But this can be done in situ, and we're hoping that this is possible in 1 week. the student project we have on that. Another student project is about, because this is really important to us, so we have like right now 2 master's projects on that. The other one is, why is it possible potentially to avoid field emission in the very first place? So what we know that the emitters are micrometer sized to submicrometer sized. It's basically dust. Yeah? What we know is also that previous studies say that it's apparently charged. Okay, there are many elements in there which could cause that. But if it's charged, and we know which way, whether it's positive or negatively charged, this dust, we could potentially use a DC, basically a barrier, a voltage, yeah, to prevent it from happening again. This is what Alvin's project is about. She tried to find a way how we can really avoid field emission in the first place. Right. I skipped one slide. Yeah, so this is some results from here where she collected. Basically, first of all, we want to understand what it is. So she collected some dust. See here the where the material science comes in. We got, that's what we found inside the link. And it's kind of wide range of materials, of metals and other elements we found in here, which was discovered by a technique called EDX, electron dispersive X-ray analysis, something which can be directly do on a scanning electron microscope. All right. Now, look to the future, look like more about ultimate performance. So let's say we have overcome these extrinsic limitations such as field emission. So how far can we push the accelerating gradient? So you know already that supercurrents only flow within the first few 100 nanometers or so. So this is then really the surface area which is the most relevant for us. In niobium actually lasts it's only 30. So, and if we look at this niobium surface, if you look at that, you will see it will not look on the nanometer scale as a very clean metal. No, we have hydrocarbons, we have different niobium oxides, and they really have very different properties. Some are weak superconductors, some others are normal conductors, others are dielectrics, and you got some of the niobium oxide going in as precipitates into deeper the layers. So this is how a realistic niobium surface could look like. The interesting thing is really that with surface engineering, yeah, just by baking it, you have a huge effect. So this is like if you have a good cavity, you have done everything right for that one. Everything is clean, no field emission, good thing, everything. And then you just bake it for at 120 degrees for 48 hours. It goes here. It's a huge difference, as you see there. I mean, like in that, it's orders of it would be orders of magnitude here, but not of magnitude. This makes a huge difference. I mean, this is not economical here, just like to operate it. You really want to be around there, the 10 to the 10 range, because you need to cooling. And then, one thing is if you just bake it 4 hours and at 75 degrees and then go to 120, you go here. You put in a little bit nitrogen in the process. So this is all like very small, subtle changes to the whole preparation process which have a huge effect on both quality factor and accelerating gradient. But going really beyond that, we see that we are reaching the ultimate limitations here. This is a superheating field. You cannot go beyond that. This is not possible. Right? This is the end of the metastable operation. You see, some are actually in the metastable range already. Yeah? But this is where you can go. So besides that this is only done for his elliptical type of cavities like that, we don't know exactly what is the best treatment for coaxial cavities. They have different field configuration, different frequency, so we cannot just use a treatment straight away for that. We have a research program, a Triumph dedicated to that, but okay, due to the constraints of time, I cannot talk about that. I go straight into how do we go beyond 50 megavolts per meter. How am I doing for time? Let me see if you clock somewhere. 5 minutes? All right, I can cope with 5 minutes. Okay, all right, that's good. 5 minutes. All right. So in that case, what we want to basically do is we want to go what we call a heterostructure. So the idea is, if I have a very, very thin superconductor exposed to a parallel magnetic field, it can withstand a much higher magnetic field. Okay, a very thin one. So the idea is that I use several of these layers separated by small insulating layers, And each of them can remain in this flux-free state and then shielding the bulk of it. So it could be a niobium cavity and having several layers on top of that. Each one remains. And then the field here on the surface there would be much smaller than the applied field. And by that, I can push to much higher accelerating gradients. Okay. So where are we with that? This is a magnetometry measurement. So it basically, the straight line tells you perfect diamagnetism. And that would mean I am in the flux-free state. So I apply a field, and as soon as I starting to drop off here, this is where I go into this mixed states where I got fluxoid. So I have a bare niobium one. Okay, this is right at HC1. Like if you do all the right sample size, you look at all the effects correctly, you see like you get this one. And then you add a multilayer. Yeah, and you can increase it. Right, great. Yeah. However, if you look at that in a radio frequency, quality factor versus accelerating gradient with a multilayer, it doesn't look very good. So we got here like the losses are huge, unfortunately. So it does not work on a radio frequency field so far. So what do we think? What's happening? We think that probably the surface layer will allow some flux to enter, that it really this does not really work. So what do we want to do? We have 3 experiments where we want to combine to get a full picture. So the first one, I told you in the beginning about this beta NMR, beta detected nuclear magnetic resonance. This is a depth resolve technique, and you can use NMR techniques in a way to get magnetic fields, somewhat indirect, but you can. And we have this specifically built spectrometer which can go up to the fields which we are interested in and can measure really magnetic flux penetration on a nanometer scale. And at this field level, this is the only facility worldwide which can do that. So you want to see, like, is there really flux entering? Then the second is, of course, you want to correlate that to your material, see if there are cracks, however your material looks like. And for that one, we can use transmission electron microscopy compared in this also with this EDX technique, tells you about the elements. So this is how it looks like. This is a very good film. As you see here, you got the layers well separated. So niobium titanium nitride, on niobium well separated. On the top is just a protective layer. But then you also want to see, like, what is the field really on substrate, how much is being shielded. For that, you can use much simpler techniques. You can actually set that up at UVic. So my PhD student has set up a magnetometer, which can really, but it can really do these measurements. So the combination of these 3 should give us insight how we can go from the current way we do SRF right now, niobium, to a multi-layered, This is how a perfect SRF cavity material would look like. You got these multi-layer for high field. Also, niobium is not a perfect thermal conductor. It would be good if everything can be on copper, and then you would even optimize both sides, actually. One for perfect heat contact to the surface, and the other one to avoid field emission and so on. So this is how an ideal SRF cavity in the future could look like. All right, so as I go pretty quick. This was an undergrad project, but I'm together with a theorist professor. And what is really interesting about that, I said, okay, we have these really high quality factors, 10 to the 12. At low field, they are not as good as they are at high field, but still pretty high. So these structures they can use in 2 senses. You can either use them really for quantum hardware potentially, or maybe loss models to understand how actually photons are being lost in quantum hardware. And what we found out is that in the niobium oxide, we have very specific energies. It looks like we have atomic-like and not glass-like loss mechanisms in here. This is my summary, which I think I can just leave here as it is and open up for questions. Thank you.